All right. So we can jump right in. Before we continue with new material, I do have to clarify one thing that might be helpful for you guys. Um, and that is the kinematic equations that I gave you last time are more general than I made it out to be. So last time I gave you this formula for when objects are experiencing free fall. They have the kinematic equations. I cannot write. They have the equations r of t is x of t in the I hat direction plus y of t in the j hat direction, where x of t is v naught in the x direction t plus x naught, and y of t is minus 1/2 gt squared plus v naught in the y direction t plus y naught. Now, this is true. However, there are more general cases, or we can apply the same reasoning that we used to get here to the more general case of just an arbitrary constant acceleration. And so, more generally, what we can do, and hopefully you guys can see how this follows, we have r of t, again, it's x of t I hat plus y of t j hat, and then we have that x of t is 1/2 a in the x direction, t squared, plus v naught x in the, or v naught in the x direction, plus x naught. Then we would have y of t is 1/2 a y t squared plus v naught y times t plus y naught. And then we would also have, for the velocity, we would have v of t is vx of t in the I hat direction plus vy of t in the j hat direction, with vx of t being ax times t plus v naught, and vy of t being ay times t plus, sorry, that's v naught x plus v naught y. So this is the more general kinematic formulas that you'll be using, especially if the acceleration is not just gravity downward. But hopefully what you can see is that if we choose, if we're working in the situation where g, if the acceleration vector, if that's only, they're not, they're just more general. If the acceleration vector is just minus g in the j hat direction, i.e. if the acceleration is just downwards with magnitude g, then this spits back out the equations that I gave you before. This is just more general. So notice that here there is a 1/2 ax t squared. That is the x, that in the equations I gave you before, that term wasn't there because in the standard coordinate system, there is no x component to the gravitational acceleration downward. But in general, in general, the acceleration vector is ax in the I hat direction plus ay in the j hat direction. And you could extend this out to the z direction as well, but we're not going to worry about that. All right, so I just wanted to introduce that. There's nothing particularly new there, it's just more general, but I just wanted to make sure I covered that in case it wasn't clear. All right, so now I'm going to continue with what we were talking about last time. We were talking about forces and Newton's laws. I'm going to have to go pretty fast today because we have a lot to get through so that you can do your homework. And I also might run over a few minutes, but hopefully that's okay. So we talked about Newton's first law, but we didn't actually talk about, and we talked about what forces were. What we haven't done is we have not talked about what types of forces there are. So we're going to do that. So the types, so there are a few different types of forces. So there are fundamental forces, and then there are non-fundamental forces. That's a pretty straightforward dichotomy. So there's a way that we can distinguish whether a force is fundamental or not. So fundamental forces can act at a distance. So this is without contact. And non-fundamental forces can't. So the example is, say, gravity is a fundamental force. And the reason we know this is that the falling ball, or a falling ball, is pulled downward by gravity without touching the Earth. So that would be an example of acting at a distance. You have two things that are not connected in any way, and the force can be transmitted from one to the other across that distance without being connected. That's what makes a force fundamental. There are other examples of fundamental forces. That would include electromagnetism, which you'll hear about in 9C. And there's also these things called the nuclear forces. Now, the nuclear forces you won't see in the 9 series. They're more advanced and they're basically quantum in nature, but they do exist. Now, there are other non-fundamental forces that I can list. And hopefully today we'll be able to go over at least some of them. I'm just going to tell you their names, but then we have more to go over before we continue. So there's tension. So this is a pulling force, say transmitted by a rope or a string, like this is pulling on something. There's the contact, also known as the normal force. This is a pushing force resulting from direct contact. From direct contact of two surfaces. So the way to imagine the normal force of the contact force, and I'll use that language interchangeably, is when one object pushes against another, there is a force between them, assuming they're not just both floating there. Like, for example, I'm sitting in my chair because I'm being pulled down by gravity, so the chair is pushing up on me. The reason it's called a normal force is because the force is always perpendicular to the surface. So if you have two surfaces touching like this, the force will be upward or downward. It'll never be shear. There's also friction, which is a force caused by rubbing of two surfaces. And it opposes, this is important, it opposes relative motion of the surfaces. Or in the case of static friction, it opposes attempted relative motion. So again, if I have two surfaces, if this top one is moving this way, friction will act to push it the other direction. There's also air resistance. Air resistance is just friction with air. And then there's a whole lot more. And we'll see some more. We're not going to see all of them, but we'll see some more. Now, before we go into details about those forces and actually how to describe them mathematically, we need to actually talk more about Newton's laws. So far we've talked about the first one, which is that an object in motion stays in motion and an object at rest stays at rest unless acted upon by an external force. The next law that we're going to talk about is, well, we're going to skip the middle one. We're going to talk about Newton's third law. So Newton's third law is just the statement, and this is probably how you've seen it before in high school. For every action, there is an equal and opposite reaction. Now, it's a relatively simple phrase, but there's a lot to break down. There's a lot to break down here. So first, let's start working through some definitions. So an action, when we say action in this definition, we mean a force from one object to another. For a reaction, what we mean is a force from the second object to the first. word equal in this sentence means the magnitudes are the same. And then when we say opposite, as an opposite reaction, what we mean is the forces, because they're vectors, forces point in opposite directions. And forces have to be vectors, by the way, because and we'll explain why that has to be the case here. But just take my word on that for a moment. If one way to see that, as I described, the contact force between two surfaces, the force points in a direction because it's pushing on something in a direction. So of course it's a vector. So when we say equal and opposite, what we mean is that there are two forces at play. So for every force that, let me just give an example, rather than having to talk in abstracts. So let's say I'm sitting on a rolling chair. So here's me. How do I draw someone sitting? Something like this. I'm a terrible artist, I'm sorry. And let's say, so I'm sitting on a rolling chair, and I stick one of my legs out, and I push off on a wall. So what force makes me move? So I push off on a wall and I would roll back, right? So the answer to this question seems kind of counterintuitive. The force that makes me move, the force that is applied that causes my motion, is the wall pushing back on my legs via a contact type force or a normal force. So what happened is I applied a force to the wall by pushing on it. I used my muscles to apply a force to the wall that pushed on it. Now the wall didn't move because it's stuck in the ground, right? And it's, buried and really heavy and things like that. But I can move. And so when I apply a force to it from Newton's third law, that is a force that's being applied. So there is an equal and opposite force applied from the second object, the wall, to the first object, me. So when I apply a force of, say, 10 newtons to the wall, and we'll talk about forces and their units in a bit, if I apply a force of some magnitude to the wall applies a force with the same magnitude back on me in the opposite direction. So by me applying that force to the wall pushes me, and there's nothing stopping me from moving. So I just move backwards. The reason the wall doesn't move is because it's fixed in the ground and it's heavy, and it's buried and it's attached to stuff. Otherwise, the wall would move, right? So the force phrase in this example for the force that made me move, remember I talked about a force phrase at the end of lecture last time, would be a contact force on me from the wall. Now, an important thing to note is that, stop getting bigger. Forces only affect the motion of the object on which the force is applied. That's important because some of you might be thinking, well, the force I applied with my legs is the thing that made me move. But that can't be the case, because the force applied by your own legs is not a force acting on you. It's a force that you are causing acting on something else. Wait a minute. Affect the motion of the object on which, sorry, I wrote the same thing that I was saying, on which it acts. A force cannot affect the thing that is causing the force. It can inadvertently affect it by, say, producing a reaction force from Newton's third law, but it can't directly affect it. So we call pairs of forces like this, where you have me pushing on the wall and the wall pushing back on me, third law pairs. or at least that's what I will refer to them as. Third law force pairs, rather. Because they always come as pairs, right? Every action has an equal and opposite reaction. And so if you want to figure out what the force pair is for a given force, you just swap the on and the by in the force phrase. So there's one force, there's the contact force on me from the wall, and then its third law pair would be the contact force on the wall from me. I'm just swapping which one is where. Okay, so we now have the tools to actually talk about force or free body diagrams. So again, this is language that will be interchanged. A force diagram or a free body diagram, they're the same thing. So our best tool for analyzing forces and their effects on motion is this type of diagram, this thing called a force or a free body diagram. So this is a diagram. This is a diagram with a single object. That's important. What does that sound? Oh, a cat wants to get in. With a single object with arrows representing force vectors drawn on it. So there's a set of rules, and then I'll give you an example. Do you guys want to meet my cat? His name is Oliver, and he's a business cat. Come here. I guess he wanted attention. This is Oliver. He's a very whiny baby. He's very good. He's also very big. And I guess he wanted to come in, but he really didn't want to be in here. I don't know. He used to be a chonker. He lost 3 pounds. Now he's only 12 pounds. Right. So we were talking about the rules for a free body diagram. Right. So there are some rules. So first, it includes only a single object. So usually this is represented by a square or by a dot or a square, right? There are force vectors, and those force vectors must be real forces. Force vectors, sorry, timer, must be real. So you're going to hear things like centrifugal force or something like that. So that's you may have heard that that's not a real force, and it's not. So you wouldn't include that on a force diagram. So this means when I say a force vector must be real, it means that they must be able to be described by a force phrase. Describable force phrase. That just has to be the case. If it can't be described with a force phrase, then it doesn't go in a free body diagram. Another rule, only forces on the object are allowed. So you don't draw on your free body diagram forces that object causes, but you only draw forces on the object when those forces are applied to that object. Fourth rule, which will be amended later, the location of where the force is applied, like if it's applied to the bottom of my feet or to my chest or whatever, doesn't matter yet. So just draw them all from like the center of your dot or something. But later it will matter. So I can give you a good example to talk us through this. So let's talk about tug of war. Tug o' war. So in tug of war, you might ask, how does it actually work? How does either side win if they both experience the same equal and opposite force, right? If one person tugs on the rope, then they're tugging on the group on the other side. But then that means that there would be an equal and opposite force of that group tugging back on the rope and thus tugging on the first side with the same force. How is it that one group wins out of the other? Well, we can do that by drawing a free body diagram. So imagine that this is a person holding a rope. I'm actually going to draw a picture here, which you can sometimes do. I don't advise it, but you can sometimes do this just to indicate the what's going on. So on the one side, you have this person's holding onto the rope. You have the rope pulling on the person. This is tension on the guy. So this is rope tension. So remember, tension is a pulling force, and so this person is holding the rope, and so the rope is because the rope has tension, it's pulling on them. So that would be one force. I draw a dot and put and an arrow representing that force. Another force coming from the center of mass, this would be gravity on the guy from the earth. You guys hear him? There's also two forces from his feet pushing upwards. So there's a contact force on the guy from the ground. And it's duplicated over on the other side as well. And then last but not least, there's a friction force pushing on his feet. This is friction on the guy from the ground. So the question is, and by the way, the more standard free body diagram for this would be something like this. You have one arrow for the tension, one arrow for the friction, little f. You have an arrow for the normal force of the contact force, and an arrow down for gravity. This is how you would draw this if you were trying to abstract away from what's actually happening. And we'll get to more details on that in a minute. But then the question is, how do you tell if this person wins or loses the tug of war? So the way that we do that is we ask, well, so the tension force between for both parties, we'll talk about friction specifically later. This is just an example. The tension force between, like, there'd be an identical force diagram on the other side for the other person on the other side of the rope. The tension force is the same. They both are pulling with, like, the tension force from Newton's third law is, the tension force from Newton's third law is the same on either side. So the difference between the two parties is the friction on each person from the ground. So whichever person has more friction, they're the person that wins, because it means that they are able to resist the tension force more. And so if one of the parties has, or if there's a very large tension and only one of the parties has more than enough friction to overcome it, the other person will just slide. And so the way that you win tug of war is you dig in to increase the amount of friction that you have. And so what you do is you apply a bigger force to the earth. You basically push in at an angle. You apply a larger force to the earth, so the earth applies a larger frictional force back on you. That's how you win a tug of war, and that's what all of your intuition says. All right. We still have quite a bit to go. Let's move on to Newton's second law. And this is all going to come together today, by the way. Like, we'll bring all of this together again at the end of by the end of lecture. The force of you pulling on the rope. So that's not so the force of you pulling on the rope, that's not a force that is affecting you. The only forces that are affecting you are the force of the rope pulling on you, the frictional force, the gravitational force, and the contact force. The force that you pull on the rope with, that affects the tension of the other person down the line. And so it will, and so the force that they pull with will affect the tension that you feel, but those numbers will have to be the same. Tension gets a little bit tricky, and we'll talk about it in more detail later. But the bottom line is we only worry about the forces that are acting on the thing that we're concerned with. Right, Newton's second law. So already we know that we can only have accelerations if the forces are present. The reason we know that is from the first law, which says that you can only go from rest to not being at rest, or from in motion to speeding up or changing direction, if there's a force present, if there's an external force present. That's what Newton's first law is about. And so we can actually now analyze the forces on objects from the others mathematically. So we need to be able to quantify their effects mathematically. And that's what the second law is. So it is the math version of the first law. You can kind of think of it like Newton had this good idea like that he had in his head, which was the first law, and then he's like, oh, well, let me just write down a math formula for it, and that was the second law. So we know force is not related to velocity. right? The first law says that a constant velocity, something moving with constant velocity just keeps moving, and it never stops. So force doesn't have to do with velocity. It can't, or at least not directly anyway. Like the force is not the thing that controls directly the velocity. The force has to do with changes in velocity, going from rest to not at rest, or going from moving in a straight line to moving in a curved line, or going from moving at a constant speed to moving at a different constant speed. The first law, so let me summarize this. Scroll, will you? There we go. First law talks about changes in velocity. That's what requires an external influence. And we know what a change in velocity is. That is acceleration. So what the first law really tells us is that things only accelerate if there's a force. So that's already getting somewhere. We need to be able to figure out how much things accelerate, though, given a certain force. And we should have some intuition. Heavy things accelerate more slowly for the same force. Than lighter things. So what did Newton conclude? Just by using that intuition, he concluded that the acceleration should be equal to the force acting on the object divided by the mass of the object. So if the mass goes up, the acceleration goes down, even if you have the same force. And we know that the force should be in the same direction as the acceleration. They're both vectors. So this is a sensible first guess. So let's talk about units first. So by the way, there's this notation that's used for units. You put the symbol that you're working with, the mathematical symbol, you put it in square brackets. And so that would mean, so this thing is equal to the units of force, since capital F stands for force. Now, so the formula that we have, this is the guess, this would say that the units of force should be equal to the units of mass times the units of acceleration, right? You can multiply both sides by the mass of the object, and you would get that the force should be equal to the mass times the acceleration, which is what we're gonna work with in a minute, by the way. But so that's the claim, but let's talk about units. So the units here, the units of mass are kilograms, and the units of acceleration is meters per second squared. So we have this new thing. So this is kilograms. Sorry, those shouldn't be in square brackets. This is kilograms times meters per second squared. And so this is kilogram meters per second squared. And so we give this a new name. We give the name of a Newton, also abbreviated with a capital N. So that is the unit of force, and it's obviously named after smart boy Sir Isaac Newton. And so the point is that this is why is one in brackets. So the parentheses are just regular parentheses. Brackets mean brackets equal units of stuff inside. That's what brackets mean. So if I put like an M for mass inside square brackets, that spits out kilograms, because those are the units of mass. Now, there's a quick note to be made. The force, both the force and the acceleration are both vectors. Are both vectors, and mass is not. So what we end up with is we get, or rather, so we have a vector equation. This is an equation relating two vectors to each other. We have that from this equation here, that the acceleration should be equal to the force divided by mass. And this is a totally valid vector equation too, right? Because you can always multiply or divide a vector by a number. You can't divide a vector by another vector, but mass is just a number. So what this equation tells us, that the acceleration vector points in the same direction as the force applied. Which of course it should. If you push on an object that's at rest, it should accelerate in the direction that you're pushing it in. One thing to just be super clear on here, mass is always positive. So you can never flip the direction of the force vector by dividing by a negative mass. Now, it turns out that this is just correct. Well, it's almost correct. I'll put a box around the one that's perfectly correct once we get there. But it turns out that this was a good guess by Newton. It's almost exactly true. So let's answer some more questions. What if there are multiple forces all acting on an object? Like in the tug of war example. Which force is the one that does the acceleration? That's a totally reasonable thing to ask, right? Well, the answer is we have to be democratic, and we just say all of them do it. They all do the acceleration. What we do is we combine the forces using vector addition. Because they are vectors, we can add them up. And use that thing, and use that combined force. The name that we give for this composite force is usually called the net force. And that is what fits into the equation. So really, if we wanted to be more precise, really our equation should look like A equals F net divided by M, right? By the way, M is the symbol that we usually use for mass. I should have made that clear. And it doesn't, and so you actually have to be careful here, because M sometimes will mean meters, sometimes will mean mass. So you have to be careful. Mass just being how much stuff there is, right? It's a measure of how much stuff there is. So what about where the force is applied? Well, if we discount rotation, the location of where the force is applied doesn't actually matter. Now, you guys all know that if I apply a force down at the bottom of this pen by like pushing on it, the pen will rotate, right? And that's because the force actually does matter. And we'll talk about how it will affect it later on in the course, but we're just not there yet. We'll talk about that in a few weeks, I think. So we assume that all forces, sorry, we don't assume that. Rather, if we discount rotation, the center of mass, and we will accurately describe or mathematically describe what the center of mass is of an object later, the center of mass of the object is the thing that accelerates. And I'll explain why I need to bring this up in a minute when forces are applied. So really, and so this center of mass, we're going to call it, we often abbreviate it as Cm. So really, what we should have is this equation. A sub Cm, that is the acceleration of the center of mass, is equal to F net divided by M. Now, so at this point, now that we have this equation, the force diagram should make sense. What the force diagram lets us do is it lets us visualize which forces are present, which forces can add together to give the net force, and then it will tell us how the body responds to those forces being applied to it in the form of giving us the acceleration of the center of mass. Now, I want to be clear here of what the center of mass is. You're probably familiar with it in colloquial language, but basically it's kind of like an average, or it's kind of like the average position of where all of the mass is on the object. So like for this pen, it's a little bit heavier on this end than it is on this end. So the center of mass would be somewhere a little bit closer to one end than the other. because you have more mass concentrated on this end and less mass concentrated over here. The reason we do that is because things tend to rotate around their center of mass, and we don't want to talk about center of mass. Sorry, we don't want to talk about rotation yet. And if you talk about the center of mass accelerating, if the object really is just like a whole thing, if it's all connected, if the center of mass accelerates, so does everything else, but it doesn't cause rotation. Whereas if just the bottom of this pen started to move, then it would move, but it would also rotate, right? If you only accelerated the bottom and didn't accelerate the top. So, but if you just push on the center of mass, like I'm doing now, I'm pulling on the center of mass, the thing doesn't rotate. Whereas if I pull down here, the thing rotates, right? So that's why we worry about the center of mass acceleration. And so for the most part, just assume the center of mass is in the thing. The center of mass of a donut is not actually within the donut. That's a good question. Center of mass is in the middle where there is no donut. The center of mass is just an abstract position in space. And we'll actually talk about this in more detail later. But we do have stuff to finish today. We still have to put together these things, put together these laws. So let's do that. Let's put together Newton's laws. Putting Newton's laws together. Right, so here's a question. If I swing a rock on a string, don't do this, by the way, only do this in Minecraft. If I swing a rock on a string in a circle around my head, think like I have a string and then I swing it around my head. You don't do it in Minecraft. I was just saying, I was just trying to indicate to you guys that you shouldn't do it in real life, and any violence that you cause should only happen in Minecraft. But ignore that. Don't do violence, it's bad. Only do violence in Minecraft. Right, if I swing a rock on a string in a circle around my head, so like I'm holding the string, I'm swinging it around, so it's going around and around and around. The question you might ask is, what happens to the rock if the string breaks? So we can answer by applying Newton's laws. So first and foremost, what we know is that there is a force, or we can consider a few things. What's making the rock go around in a circle? Well, clearly there needs to be a force involved, because a circle is not constant velocity straight line motion. And Newton's first law tells us that if an object an object will move in a constant at constant speed in a straight line unless there is a force acting on it. So because it's not moving in a straight line, there has to be a force acting on it. Now, what could it be? Well, there could be gravity. That certainly plays a role. Gravity will basically act on everything. However, there's another force. It's connected to a string, and that string can apply a tension force. And so that tension force is what's going to be causing its circular motion. Now, what happens if that tension force stops? Well, first, we know that gravity will still be there, so it will fall. But what happens to its, like if you view it from above, what happens? Will it keep going in a circle? Will it spiral out? What happens? Well, we know the answer to this. It has to be going at a constant velocity, or constant speed straight line. If there's no force in, say, the horizontal or vertical directions, it just goes off. So you're right, it flies off in a tangent. So it was going around in a circle. Hey, here's another cat. Oh, no, he just ran away. It was going around in a circle, and then it breaks. The rope snaps here. So then the rock just goes off tangent, because that's the direction it was going down. And then you're right, then it accelerates, and then it continues to accelerate downwards, but it goes off in a straight direction. I have one, my sister-in-law has one. But, you know, my sister-in-law lives with me, so 2 cats. I have 2 cats. I wish I had all the cats. Cats are great. Another example. What about pulling a spool? So you have a spool with a whole bunch of string wrapped around it, and there's string coming down, and you pull. what happens to the spool? Does the spool go up, or does the spool go down? Does the spool just rotate? Well, there's a few things that are required here. If you were just pulling on the spool, then there'd only be one force applied on the spool, so the spool would come down with you. In order to keep the spool from falling down, you need another thing holding it up, and that is the axis of the spool. So you pull on the spool on one side, that applies a force downwards to the spool. So in order to keep it up, you need a countering force pushing it back up, and that's a contact force between the spool and the axle. Another example would be two people pushing on a wheeled cart that isn't moving. So another example might be you have a wheeled cart. One person pushes this way. That's a really long arm. The other person is pushing this way. They both have really long arms. Geez. They're like chimps. So they're both pushing on a cart. Why doesn't the cart move? Well, the cart doesn't move because the net force is 0. There is a downward force from gravity, but that doesn't affect it because there's an upward force from the normal force, so it's not falling to the ground. And the reason why the cart doesn't move left or right is because the forces on from either person are the same, and so the net force is 0. Another question is, what happens if we drop a stone, what happens to the Earth? Right, so we know that every action has an equal and opposite reaction, right? So that means that, yes, the Earth is pulling down on the stone. It causes gravity to act on it. Sorry, the Earth's force acts on the stone. No, so we're just dropping the stone. While it's falling, the Earth is pulling down on the stone. So Newton's third law says that for every action, there's an equal and opposite reaction. So that means that if we swap the force phrase, force of gravity, on the stone by the Earth, the equal and opposite reaction would be the force of gravity on the Earth by the stone. So in fact, the stone pulls up on the Earth as the stone is falling. So in that case, the Earth actually moves up a little bit. Now, the Earth is so much heavier than the stone, so it doesn't move up in any measurable amount, but it does happen. It must happen. Right. So I need to introduce one more concept, just to erase any confusion that you may have had, because this is an annoying pet peeve of mine, which is the idea of inertia versus static friction. I actually got into an argument about this with a friend of mine, and I had to tell him, look, I teach this to my students. Trust me. So there's a difference between these things. Yes, inertia is a property of matter. I'm surprised you guys are old enough for that. That was like when I was in 2nd grade is when I watched Bill Nye. Isaiah, you would need like enough mass in the form of rocks that are like equal to the mass of the Earth. And the trouble is you can't really, like, the rocks used to be part of the Earth, so by pulling them up and dropping them, you're not really going to affect the Earth's motion. Anyway, so let's ask, what is inertia? So inertia is not something to be overcome to keep something moving. So the important point is people will say like, oh, that speeding truck had so much inertia. How do we, or this truck has so much inertia, how do we, like, we need to overcome its inertia in order to speed it up more. Like, that's not what inertia is. All inertia is it's a fancy word for mass. That's literally all it is. They are identical things. Anytime somebody says inertia, replace it with mass, and if it doesn't make sense, then they don't know what they're talking about. So the question then is, what resists motion? So like the example is, people will say things like, why can't a human being just push something that's really heavy? Oh, it has so much inertia. You have to overcome its inertia to get it moving. No, that's not true. So what is it? What does resist motion? What does, sorry, I should underline it, does. What does resist motion if something is pushed with not enough force? I'm going to put that in quotes. So think pushing a really heavy box. Like, what is the thing that prevents the thing from moving? Bingo, it's friction. So in particular, it's static friction. Particular. So static friction is calculationally related to mass, but it's not mass. So the mass shows, if you're trying to compute the static friction that is active or that can act on a body, the mass of the object will show up, but that's not the only contributing factor. And one way to see this is that it's easy to push, maybe not easy, but it's possible, it's easy to push a Boeing 747 on ice. And the reason for that is that the other factors in computing static friction, things like how slippery an object is, that's a factor that will play a role, is very, like, it makes it so it's a lot easier to push something because ice is slippery. Whereas it would be a lot harder to push something on like concrete or rubber flooring. All right, so the last thing to keep, so I think instead of talking about specifics of gravity or specifics of forces, which is what I was going to do, I think I'm just going to do a quick example of these, of like using free body diagrams and Newton's laws, just to explain, just to give you a little bit of a hint or help for the homework. So let's just draw a free body diagram, and I'm just going to draw some random forces on it. I'm going to label them F1. Maybe this one's F2. And then, why did I put the 2 down there? And maybe this is a 45-degree angle. And then we'll have one that's, I don't know, downwards here. This will be F3. And I'm going to tell you, so let's say that the mass, let's say, is 5 kilograms. Okay, let's say that F1, let's draw some axes. So this will be the x-axis, this will be the y-axis. Just that way, then we can write out our vectors. This is just some random example. I'm just drawing. I just gave you a free body diagram. I'm putting the forces, and we're going to compute the acceleration on this object. So F1, let's just say it's 3 newtons in the I hat direction, and we know it points to the right, so there's nothing else in the j hat direction. F2, and I'm just coming up with these numbers off the top of my head. Let's say F2 is 5 newtons in the I hat direction and 5 newtons in the j hat direction. It's 45 degrees, so the force has to be the same amount in the x and y directions. We could, if I had only given you the magnitude, we could have worked this out. Right, we could have like drawn a diagram if this was 5 times square root 2 newtons, and this is 45 degrees, we could have worked out the components, right? So this would be 5 newtons, and this would be 5 newtons. F3, let's just say well, we know it points in the downward y direction, because it's from the diagram, it's pointing downward. So it should be negative, and let's make it -4 newtons in the j hat direction. All right, now let's go and find out what is the net force. Well, all we do is we add up all of the forces. So we add up the I components, add up the j components, write it out. So this is 3 newtons plus 5 newtons in the I hat direction, plus 5 newtons minus 4 newtons in the j hat direction, or it's 8 newtons in the I hat direction, plus 1 newton in the j hat direction. Great, that's our net force. Now let's use Newton's second law. Newton's second law is that the center of mass acceleration is F net divided by the mass. So the center of mass acceleration then, and this is the acceleration that this object actually experiences. This is the thing that you would plug in to the kinematic equations, assuming this is constant. This would be equal to 8 newtons divided by 5 kilograms in the I hat direction, plus 1 newton divided by 5 kilograms in the j hat direction. And now let's just back up and remember, a newton it has units of mass times acceleration. So a newton is kilograms times meters per second squared. So this is 8/5 meters per second squared in the I hat direction, plus 1/5 meters per second squared in the j hat direction. And so this is our center of mass acceleration, our vector. And if we wanted to plug it into the kinematics equations to figure out what its speed and position is after a certain amount of time, this would be ax, and this would be ay. And because these are constant, those kinematic equations are valid. All right, we ran a few minutes over, sorry about that. We will continue later, or we will continue with more stuff next week. Not next week, on Wednesday, sorry.